Something that's actually been of interest on the, actually from industry players has been, we have an area of inquiry on what we call learning for combinatorial optimization. So up to now, we've discussed more about control problems, but as I mentioned earlier, this curse of variety also occurs for combinatorial operations type problems. So one example is the very classic vehicle routing problem. So with this, you can think of Amazon's delivery trucks. Every day is routing 100,000 packages for the city of Boston and has to figure out which trucks, which packages, what order of places to visit, and trying to do this as efficiently as possible with as few trucks as possible, and so on. So this is not just one problem, this is also a family of problems that are known as vehicle routing problems. So for instance, the trucks have capacities. The trucks, as they become electric, will require charging in addition. They, in other cases, for instance, in ride hailing, they may need to pick up objects as well as drop off objects. During the pandemic, it was very important that there was a cold chain. There could also be cases where delivery is by bicycle, and these are all different variations on the same sort of central problem. And so that by itself is fine. What the challenge is that every one of these variations typically requires custom heuristics, which are very expensive, may take years to develop to actually solve these problems. These are what are known as NP-hard problems. These are problems where it is unlikely that there even exist efficient algorithms to solve, let alone us be able to find them. Okay. So what we are doing is, basically taking a learning-enabled approach. Our approach is essentially that, well, we have done a lot of work to solve some variations of these problems. It is very possible that these new variations, let's say delivery by bicycle, delivery for electric vehicles, are not that different. But right now, with sort of classical approaches, it still takes years to develop effective solutions for these variations. Our hope is that learning-enabled approaches with modern deep learning based methods can actually help us automatically identify heuristics that can be effective for these problems. And so we've actually been able to demonstrate this successfully for vehicle routing problems, where what we're able to say is that, let's say we're able to solve a small version of a problem, a small vehicle routing problem. But many times, especially in transportation settings, problems are large. We're delivering thousands, if not hundreds of thousands, say, of these packages. What we've been able to do is contribute learning-enabled approaches that can take these existing solution methods that work on small problems and incorporate them into this learning framework that's based on a problem decomposition that is able to then scale and accelerate that existing solver for large problems, and is able to do this in a way that can automatically identify heuristics for these specialized variations of the vehicle routing problem. So what we're doing now is actually we're taking some of these similar ideas and we are trying to see if, maybe this works not only for vehicle routing problems, but maybe also for multi-agent robotics problems. And so we're actually applying this to the setting of automated warehouses. We also are exploring a few directions, not only for big problems, but also for small problems. And In particular, there's a very general class of solvers known as mixed integer program solvers that are very effective. You can formulate whatever combinatorial problem you want. And if it's small enough, these tools can solve it. But once they get too large, these solvers sort of struggle. So we're also looking at sort of integrating machine learning into these solvers, these very general purpose solvers, to see to what extent we can push the boundaries on the types of problems that they can solve.